mountains, goodbye to the sea, leaving behind all that was home to me. The earth grows smaller, a memory in blue, as I chase the light of a star so new. I'm bound for a distant star, leaving behind who we are, in the silence of space where dreams collide. I'll carry your love as my guide. Wherever my North Star. I think of the faces, the moments we shared, the laughter, the tears, how deeply we cared. But the pull of the unknown, it calls me away to where night is forever and time slips away. I'm bound for a distant star, leaving behind who we are, in the silence of space where dreams collide. I'll carry your love as my guide. And though the distance grows each day, your memory will never fade away. In every star I see your light, guiding me through this endless night. I'm bound for a distant star, leaving behind who we are, in the silence of space where dreams collide. I'll carry your love as my guide. And farewell, my earth, my beautiful home. I'm taking the stars, but I'll never roam too far from the love that made me whole. Forth with me now, in the depths of my soul. Depths of my soul, make me whole.
Hey there, everybody. How are you? It is Mark with you tonight, and only me. Daryl's taking the night off. I guess it's Thanksgiving Eve, but you know something? I figured why not bring you a pre-turkey slice of the universe, right? As Dacian's always said, a slice of astronomy pie. That's a great idea. Yes, that was a new song that I wrote. It's called Final Journeys. It's about someone leaving Earth and heading out to the void to do a one-way trip to the stars. I mean, we will do that someday. So, you know, as an astronomer, I've foreseen that for decades. I don't know when it'll happen, but it ain't gonna happen like now. But it's pretty cool anyway. So that said, I want to start off by letting you know I did the focus, and we're gonna head up into the north tonight. Let me just show you the night sky out there right now. Let me bring this up. Okay, this is our night sky. These are high clouds, 80 miles out past Phoenix. This is to the southeast here, and this is the remnant of the summer Milky Way here. And we're going to be looking up in the north, which is right here. Okay, and so we're going to be way up here looking at some cool things up here, and it's kind of neat. So we'll check that out too. And maybe we'll get to some pre-winter stuff. I'm going to try not to go too late because everybody's got to get up early, you know, in the U.S. anyway, who celebrate Thanksgiving. There's people watching from around the world who say, Thanksgiving, what's that? Well, you know what it is, but it's nothing that you participate in, and that's okay. All right, so let's do this. Let's come over here And I'm going to take us first. I'm going to take us up to the Andromeda Galaxy just to set a location. You can watch the telescope up there moving. Okay, let me pull this down. This is dead center in the way. There we go. All right. And in here, we should see the Andromeda Galaxy just slip in as a fuzzy object. Oh, it won't yet because I forgot to do the other rest of the setup. So we'll just wait it out for a second. SkyTour fan says, I'm going to quiz you. How many asteroids are there in the solar system? Well, I have to tell you, the number of asteroids in the solar system probably numbers in the hundreds of thousands for any fairly substantial size. And then probably, if you consider collisional planetesimals that have been knocked off of, or little mini asteroids knocked off of them, I'd have to say we're probably looking at least 1 million objects out there anyway. And that's not exaggeration. That's actually pretty accurate, you know. So let me just take care of this little thing here first. I'm going to add in my correctional values here so I can... This is usually done before I start, but I figured I'd start right away today. And then, you know, that way I can end quicker so you can all go to sleep quicker so that you can stuff yourselves to the gills, those that celebrate Thanksgiving. Okay, here we go. All right. Okay, and then the last but not least, I'm going to turn off this high precision thing, which doesn't really do what I want it to do. And it works very well without it. So that's good. So now we go back and you'll see our guiding numbers. There they are. All right. So now if I come back into our planetarium, you can see that there is our crosshair. Okay. And if we zoom in on it, you can see that that's where Andromeda is right there, but we are outside the field right now. So I'm going to tell it to go to Andromeda, and it'll now bring us back into the middle, and you'll start to see the fuzzy object now show up here in just a sec. There it is. And it'll kind of work its way back in. So this is the Andromeda Galaxy here. The nucleus is right here. I'm going to move it over in just a second and show it to you in more clarity. I'm getting really excited about the Benson telescope. I gotta tell you, it's really starting to hit home how amazing that's going to be out there. You think this is a dark sky when you see this beautiful starry sky here, okay? But Benson, the Milky Way, is even darker, if you can imagine that. And the sky is just stunning. Yeah. Okay, so there's the center of the galaxy. Let's move over. And I'm going to do something I haven't done. I'm going to actually take a nice photograph centering the center of the galaxy. All right, you'll notice this fuzzy thing up here. That is Messier 110. And then this one down here, that's Messier 32. And this is Messier 31. The galaxy itself. All right, so let's park it up here a little bit. All right. And the thing is, you don't have to believe me if you don't want to believe me on that. I can just bring up our captioning system and show you. Here's the Andromeda Galaxy. There's Messier 110 and there's Messier 32. Labeled for all to see. Okay. And now let's move just a little bit more to the west. You know, a little bit north too, because I want Messier 110 to be just a little bit, you know, more fully in the field. So now we'll see the family of all 3 galaxies in one shot. Okay. All right. So, I've also recalibrated the colors. So the colors are now going to be absolutely perfect. They weren't before. And things that were showing green should have been actually showing as teal, which the green was the oxygen 3, the doubly ionized oxygen. And it should now show as blue. We'll see that if we can get to the Dumbbell Nebula or the Veil at some point. Okay, let's just do a quick exposure here. Let's do a 25-second exposure here. That's 25S. Start off we go, and we'll come out of low light mode and go into deep sky mode. You can check down here in the lower right. You can see right there, that is our, well, you can't see it yet. Let me bring that up so you can see it. Let me bring it up so you can see it. It's coming. There you go. Now you see the progress bar right here. All right, and then we bring up our live stack here. And we'll see our first image here in a moment. Doesn't look like much, does it? Well, that's because we have to color correct it and do a real initial processing. Here's all the data. See it? Right there? That's all the data. And these are the bars that capture it. And we want these bars to be on either side of the data. Right now, this one is on the right side, so we're missing most of it. So if we go here, oh wow, look at that. Now we get the data. And this one is a mid-range. So the more we pull this over up the slope, we get brighter and brighter and brighter. Okay, so we typically would keep this down at the lower third of the slope. Now you got that, look at that. Now it's beautiful. All right, and as color corrected, that looks really pretty. Often, you know, I've talked about this as an astronomer, we've actually used negatives of imagery. So we'd use the negatives to exactly to do this analysis. Because if you look at here, this is much more interesting as an object because we can see that there's some other structure in here, which if we come out of the negative mode, that structure is kind of lost. You don't really see it too well. And then up here, Mesher 110, right, we see there's some detail in it, okay, but if we go to negative, you can see some other faint structure out here that was missing and some really nice detail in here. Now that's visible in the bright side, okay, when we go bright like this, like negative, but it's not as pronounced. So using a negative helps us, the negative approach anyway. So I want to say hello to everybody that's decided to join us on the Thanksgiving Eve. Michael Hedrick was the first one. That's fantastic. You win a cookie. Renee Cruz with all of her incredible Happy Thanksgiving, from the Philippines. Thank you so much, Renee. And Raul Babadia, nice to see you. SkyTour Live fan, of course, is here. And Daisy and Zoe are here tonight. I don't expect we're going to be a very large crowd tonight because it's, pre-holiday, And we have Wayne Pinkham. Hello, Wayne. Luis Rodriguez, how are you? And he says, on average, a mission to Mars takes about 6 to 9 months. Ouch. Easy, Elon. Sure, this will work out okay. As a matter of fact, yeah. Because it's just a matter of figuring out what tasks people have to have as a daily job. And that's very important. Think about this. People spend a year on the space station, right? That's a long time. On the ISS, they've spent a year up there at times. And spending a year on the space station sounds like a lot, but they're circling the Earth in a tin can. So after 3 weeks, you know every square inch of that. So what does that mean? It means that you have to have a job to do. You need a 9 to 5. You need a science job. And that's what they do. They give each other science jobs, and NASA gives them science jobs, and they go up there for a specific purpose. No one is wasted. There's no spare time. And do you know something? The cupola on the ISS, the location where they go to look out the windows down at the Earth, you think they just go and check that out all the time. No, actually, when they're on their work shifts, they can't even begin to think about going into the cupola and checking out the Earth. That's actually like at the end of your shift or when you're about to go to bed or whatever. You can't do it during your workday up there. There's just too much to do. Literally every minute is accounted for. So it's kind of interesting. Now, there's some people that are a little freer than others, like people that pay several $1 million to go up for a ride to the space station. But the other people, they have to work there. And science teams, every minute they're up there is costing lots and lots of money. So every minute is accounted for. I know, it sounds boring, huh? The life of an astronaut. Or astronaut, depending on how you think about your work. Tricia Ferreira, hi. I see Stan from Two Rivers is with us. Hey, Stan. Creeptage is with us. Astrocop, how you doing? Nice to see you. Richard Spencer, nice to see you as well. You're here from Canada. Nice. Sam S. is with us. Carl Becker, good to see you. Yeah, this is the Andromeda Galaxy right here. And I wanted to point out something again while this is exposing. We're doing a stack right now. You'll see we have... we're only stacked 2 and then 10 have been failures. And I think I have to... I got to come back and just increase the numbers just a little bit to kick my filter up a little bit. And now they'll start coming in. So this next exposure will probably come in. Yeah. All right. So while it's coming in and doing that, I'm going to just zoom in on this right here. This is Measure 110. Let me enhance it a little bit. Let me get rid of the noisiness. Boom. There we go. Look at that. All right. And I can see that our focus is off a little bit. This is a first object that I'm doing. The telescope is still cooling down to the ambient temperature of the outside air, because once the top is rolled off, you've got to give it some time, and we haven't given it that time yet. So this exposure is not a keeper. This is just a quickie. Yeah, we'll refocus and make it a real exposure in just a little while. Andromeda is 2.4 million light years away. So amazing to think that all the light you're seeing, these stars here, all these dots you're seeing, these are up here in our galaxy. Andromeda is way, way out here. It's 2.4 million light years beyond all these stars. Now, there are some things that are in the Andromeda Galaxy, like these little dots. These little guys are in the galaxy. This nebula right here, that's in the galaxy. Okay. And, there are other nebulae. This star cloud here is in a galaxy. This right here, that is a nebula that's in this galaxy. A massive nebula. Now, the Andromeda Galaxy is actually really large. We're talking about a galaxy that is has almost a trillion stars in it. A trillion. That's 1,000 billion. And when we talk about our galaxy, we have 150 billion, maybe 400 billion at the very, very high end. Okay. However, this has 1 trillion stars in it. Isn't that crazy? So, and it is heading for us in space, in the three-dimensional realm. The Andromeda Galaxy is heading toward us, and we're going to be absorbed by the Andromeda Galaxy in about 3 to 4 billion years. And our galaxy will either cease to exist or will be modified to a new shape. That's what happens when massive galactic objects collide with each other. We see that all over the universe. Galaxies in collision. It's a big slow motion thing. It's really interesting how it happens. And nothing happens, though, to life in the galaxy. If it's still there, it's going to stay there. The stars are really far apart. No stars ever collide. So it's kind of interesting. And let's see. Michael Hendrick has a question. Realistically, what year or decade do you think we might see a space hotel? Did you see the first question? Sidekick Daryl. Daryl's not here to ask. Yeah, or to see. Yeah. I guess I missed the first question. But you said in the first question, did you see the night sky while at Benson? Yes, I did. And SkyTour Radio that you asked about, we still do that every Sunday night, 6 to 8 p.m. Eastern Time. This past Sunday, I didn't do it. I was sick, so I didn't do it. I'm better now. So we'll see what happens this weekend. Hello, Stuffy. Welcome. Yeah. And so, to answer your other question about when might we see a space hotel, you got to keep in mind that we're going to have to make space travel affordable for a lot more people that would make such a endeavor viable. Right now, going to the space station is going to cost you, if you're a millionaire, many millions of dollars. And so, it's definitely unforgettable, I'm sure. But there's some people that get up to space and they can't stand it. They can't handle it. Because, I'll give you an idea. When you just go over the hump on a roller coaster and your stomach seems to go, oh, right? Or you go over a bump in the car, whoa. Okay, that feeling right there that you're feeling is called weightlessness. That's what the astronauts are feeling 24/7. They sleep like that. They go to the bathroom like that. They work like that. So imagine falling from the sky and feeling that in the pit of your stomach the entire time you're up there. Now, there's people that get used to it, but they do get space sick, and that's something that's a very real affliction. And so the people have to get used to it. There's been cases where astronauts have been unable to get used to it, and they were pretty much useless in orbit. They went up once, and that was the last time they're ever going to go, because the investment in their time on board was just not worth it, because they were useless to anyone to do work. But if you're a paying millionaire passenger, well, guess what? You can go up, and if you just sit there, being sick the entire time, who cares? You paid your way. You're not there to do any jobs. So you wouldn't be missed on the work line. Interesting, huh? And Creeptasia says, when our people travel to Mars, muscle and bone atrophy will exist. Do they have to implement a gravitational rotation structure in their craft to produce G's? Yeah, actually, that's a very good point. When I was 9 years old, I designed a space station. I know, I'm a nerd. And I sent it to NASA, and they actually reviewed it. And they said all these good points, said stick around, stay in the space program. I kind of did, didn't I? Well, bottom line is, I had a rotational system that delivered 1G at the end of a large structure that was spinning. And that is one of the designs to make 1G. And, okay, Elon Musk's Spaceship, okay, those can spin, and they actually have a manner in which they can spin at a fairly rapid rate in order to deliver 1G to anyone inside. And they'd be standing on the sides, okay? If it's heading this way to Mars, out of the page toward you, the cylinder coming toward you, they'd be standing like this with their feet on the ground this way or this way, okay? Because the thing would be spinning this way. That's one of the concepts that Musk was floating. Pretty cool. So they do want to make sure that people, in fact, will do just that. Exercise, use resistance bands to keep them held down to a treadmill so they can run and simulate 1G. But the body knows when it's weightless. And so even if you have resistance bands holding you down to a treadmill, your arms can still just float like this, and you wouldn't care. They would just float, and you'd be running. It wouldn't matter. So that's kind of interesting how weightlessness works. The body knows it's weightless. And you'll feel it in the pit of your stomach, even if you're held to something. So it is definitely something where we'd have to actually simulate the 1G, or the one gravitational quotient of gravity for a spacecraft. So if you're going to sit for 6 to 9 months and then you go to a planet with basically, just over a third of Earth gravity on it, even that third of an Earth gravity on Mars would feel like a lot of gravity if you were weightless the whole time. And you got to hit the ground running on a planet like Mars. So you'd have to know what you're doing right from day one. Okay, I'm going to back out here and let's just take a look. Look at that Andromeda Galaxy. That's gorgeous. Okay, but the problem is it's not focused, so I'm going to clear it. I know. You say, what? Yeah, we're going to clear it, and we're going now that the telescope has been acclimated, we're going to go to our low light mode. All right. And in our low light mode, we can now go to through focus routine and make sure it's all focused. I'm going to move us also. Move it up to the north. Hey, Rockstar. Rockstar's with us. How's it going, Rock? Hey, Waldo. Waldo's with us. Fantasy's with us. High Speed, Low Drag's with us. The Great Turkey Star Constellation. Turkey Star, huh? I'd love to if we had one. I don't know if we have a Turkey Star Constellation. But I like it. Jose Navarro, how you doing? Yeah, we'll come back to the Andromeda in just a minute, Jose. I'm just going to I'm going to focus the telescope again. And once we're focused, and I'll let you watch the focusing routine. So the telescope is now it's gonna make a curve. It's gonna look like a. Hey, Greg O'Brien, thank you so much. Space is littered with stars. Then how come it's so dark? Ah, you speak of Olber's paradox. Olber's, O-L-B-E-R-S. Olber has said if there's so many stars that you see in every direction, then technically the whole night sky should be illuminated. That's a valid thought process, except for one problem. If you look at the night sky, we see the stars in a photograph and you see big bloated balls like these, okay? Except stars are only points of light, okay? They're only ever tiny, tiny points of light. And the farther away they are, the intensity of that light falls off or diminishes by the square of the distance. So, for example, okay, so what that means, if you shine a flashlight, okay, from here, and you look at the light right next to it, it'll be a certain brightness. If you go 4 times further away from you, okay, a distance of 4 times further away, then that light is going to be 16 times fainter, because 1 over 4 squared is 16. Okay, so 4 times, that's called the inverse square law. Okay, so this problem is why we don't see stars in every direction we look, because the most of the stars in the universe are these red dwarf stars. And these red dwarf stars are extremely faint. You can't see them without a telescope, as it is. And then, in that case, because you can't see them without a telescope, and because stars' brightness varies so much, this is why we don't see stars everywhere we look. And the other thing is, they're not evenly spread around in the universe. There's places you can go and look in the sky where there's nothing. All right? There are some famous voids in the sky. One of them is the Bootes void, in the constellation Bootes. And the Bootes void is one of those places where you just don't have a way to see anything in there, because it just doesn't happen to be anything in that particular region. If everything was even, then that'd be one thing, but it's not. It's not. Okay, so I'm going to bring us back here. All right. Okay, so Alright, let's head back south again. We'll do this one more time. Okay, there's measure 110, there's measure 31, and then below it we have measure 32. And as soon as that comes into the view, we will... There we are. Okay, so let's go down one north, one more little bit, and then pop back. Okay, this looks good. All right. Okay, this time we're going to do a 20 second exposure. Andromeda with our telescope is literally overexposed with a 25-second exposure. It's pretty amazing. Okay, so we'll come out of this low light mode, go back into our live stack mode, and you'll see in this live stack image here that the stars are going to be a lot more well focused. It's going to look much different. Hey, Greg O'Brien. Thank you again, by the way, for that donation. That was very kind. We definitely need the help, I can tell you that. You know. Oh yeah, look at this. Okay, that little bar is an artifact of the process. If I say better quality, it goes away. So now we see. Okay, so we'll do this. Let's do a little color right there. And let's do a processing, and it'll make it a little bright. Alright. Alright, so now let's do this. Let's pull this black level up. Yeah, and again, this is our data. This is the red, green, and the blue curves, and this is the average of all three. And so we only work to the white curve. And if we bring this bar right to the left of the peak, that's about as dark as we want to get without losing any data. This is the mid-range. Okay, bring it in, it gets very bright. Okay, as you can see, boom, that just kind of shows you what's really there. And bring it back out, and now it'll soften some noise. It will allow you to play with the different elements in the shot and get it to look pretty cool. So this is a stack of 4 already in the 20-second arrangement. Hey Greg, thank you. Did you mean to do that twice? I guess you did. Yeah, this is the time machine, Greg. Greg O'Brien says thank you for sharing the time machine with us. Yeah, you know, you're seeing this as it was 2.4 million years ago. I always like to think about what was happening on the Earth at the time. 2.4 million years ago, we had some, there was Lucy Australopithecus was already 2 million years old in terms of being on the Earth, because Lucy came around 4.2 million years ago. So 2.4 million years ago, Lucy and other early hominids were maturing and starting to change and become what they would become to become eventually Homo sapiens sapiens, which is what we are. A fascinating journey it is to go back in time and look at what the Earth looked like when the star's light was just leaving. Interesting how the light we're seeing right this second, the light that you're looking at just right now on this screen, started 2.4 million years ago from that galaxy and just got here. And we caught it, and now it's gone forever. Isn't that something? Steven is with us. Mr. Django, how are you? Yeah, Greg, blows my mind too. He says, blows my mind. Yeah, it is. It's a mind blower. No doubt about it. No doubt about it. Yeah. Let me just see. I'm just going to check something here. I thought I saw... I'm not sure if I did, but I thought I saw early on. I thought I saw that Tiffany was here, but I don't think she was. Well, that's okay. Anyway, yeah. All right, so as we look at this, yeah, actually, Greg O'Brien says somebody looking at the Earth that long ago would see dinosaurs. Well, dinosaurs were gone long before that, about 65 million years ago, Greg. But that's a fair point. They would see a very different Earth, wouldn't they? They wouldn't see city lights. They wouldn't see spacecraft in orbit around the planet. In fact, the Earth would be a virgin, have virgin orbits, nothing up in there. Okay, at that time. So yeah, and I've often wondered if wouldn't it be cool if we could find a space mirror somewhere out there that could actually show us an image of what the Earth was looking like at the time that the space mirror, say a few light years away, had been looking at us. If we can focus on that image, we would see the Earth as it was to the space mirror all that time ago. I mean, pretty cool, and it's a neat thought problem. It really is. Okay, all right, we've done 14 here. Let's go into our planetarium program for a minute, and I want to do something. I want to, first of all, I'm going to change to increase our speed a little bit, and now let's do this. Yeah, we got these guys. Yeah, right. Yeah, there's a lot of really cool things that are coming up now, and I had started a lot of them. I put a bunch of them in here just so we could all check them out. We'll probably check this guy out too. That'll be our next target. And it's on the other side of the pole. There's the Andromeda Galaxy. We're going to go down here to check this guy out. It's still visible to us, but we'll get there in a minute. Alright, so this is the Andromeda Galaxy. Let's zoom in on this right here now, the Messier 110 again. What's interesting is this is an elliptical galaxy, and elliptical galaxies can be round or they can be really, really elliptical, and they have an oddity about them in that they have no dust in them usually. When we look at the Andromeda Galaxy, look at all this dust. This is not a void in the stars. This is dark dust lanes in the galaxy amid these beautiful star-forming regions here in the spiral arms out here, all right? And this dark dust, you'll see it circling around, curling around, okay? And the elliptical galaxies, like Messier 32, don't really have any of that. Messier 110, typically these galaxies shouldn't have any of that. But when we zoom into Messier 110, well, lo and behold, it looks like it has a very strange dark lane in it with some other dark lanes. A very strange thing to happen with a galaxy that's an elliptical galaxy. Normally, you don't see that with these ellipticals. So this has been an oddity. A lot of people say, wow, this is a very interesting galaxy. We need to study it more. Very cool. Okay, 20 exposures. I'm going to keep this one, so I'm going to, I'll do this. I'm going to let it label for me. I will say Messier 31, Andromeda Galaxy. I'll tell it to set that as the target, and that goes up in there. And now I can save this. I love our annotation thing. I'll save it with annotations too, so the image will be on our server. Where's our server? SkyTourLive.org. If you go to SkyTourLive.org here, you can actually pick up all these images from tonight. We provide them for free. Everything you see us take here. And when we hit save, we save the pictures, the images, and you can grab those and enjoy them. All right, so I saved this one with annotations. It's out there. Okay, so now I can save it as an astronomical file that we will analyze later, and then I'll save it as a FITS file. I'm sorry, as a PNG file, which looks just like what you're about to see. All right, so this is the file that we save with the annotations, and this is the file we just saved of the galaxy, and this is available to you for free. It's out there. If you want to join our Patreon, we'd love it. We need the help. And that Patreon will allow us to do other things like provide higher resolution imagery for you. And then here's Tiffany. Hi, Tiffany. It'll allow you to also, the Patreon will allow you to get some swag, some cool stuff from us. And if you want to know what that looks like, go to the SkyTour shop up there in the upper right here. And you can check out about 45, 50 products out there that we make. And this is, again, we're a non-profit. We don't make any money on this. I'm not getting paid for this. This is my pay. This image, this is my payment. Your comments are my payment. So that's what happens. That's where I get my money, okay? If my money's worth, I should say. All right, we'll save this one more time, and then we're going to go to the next item. The object I want to show you, which is really cool because you see this dust in here? This dust is everywhere. It's in our galaxy too. Our galaxy is full of dust, right? When you look at the Milky Way, right? Let's go check it out. Okay, this Milky Way, you notice it looks mottled. It has like darkness. See these dark blobs in here? These are dark dust clouds in our Milky Way. These dark dust clouds will break up our Milky Way, okay? This is the North American Nebula right here. This is Vega, okay, Altair, and Deneb. Deneb, Vega, and Altair form the Summer Triangle. And here is what looks like might be an aircraft coming through. In the next image, it'll be either here or there. There. Okay, so it's moving there. We got another one down here. So yeah, these are time exposure. This is a 9-second exposure that we're doing right here. Okay, and the clouds were supposed to be here, and luckily they're not. We're keeping them at bay. All right. So that said, you see that darkness in there, the Milky Way, that mottled dark dust. And in our own galaxy, you know, we see it in other galaxies like this, but in our own galaxy, it looks a little different. And I'm going to show you that. Okay, there's 30. I'll save that as the last one. And there we go. Okay. So now we'll go back into our low light settings here. And this will allow us to see the object that we're looking at next when we come into it. All right. So here's what we're going to do. We're coming here. All right. And we're going to jump to this guy right here. All right. I just told it to go there. And we're heading there now. You watch the telescope is bending way over. It's not as drastic as it looks. Okay. All right, let's see if we can do an identification of stuff here. All right, there is Hipparchus 104291, that star. And what we're going to do is we're going to center that object. (104291). So that's going to move up right into the middle here. And there's the Iris Nebula here. So what we'll do is we're going to go to the Iris right there. All right, so here's what we're going to do. I know it looks like kind of like a fuzzy star, and there's a reason for that, as you'll see in a minute. The Iris is a young star embedded in a cloud of dust that was the result of and created by supernovae in the past, and that dust accumulates and gravity pulls and tugs it around, moves it to different spots. It has the motion of its parent star from like a supernova explosion pushing outward. It collides with other stuff, makes swirl patterns, and moves on out. It's amazing how much dust there is in the universe. So let's pull this down here. and head south a bit to pull it up, because I know what's in here and I want you to be able to see it. Okay, so this is really good. So right from here, there's a lot of stuff right here. Notice that the stars look like you should see more stars. Where's all the stars in here? Is this one of those voids, Mark, that you've been telling us about? No, this isn't a void here. This is dark dust blocking these stars from being seen behind them. You should see stars right here, but there's a dust cloud in front of them, and so you don't see the stars behind here. Okay, and let's show you what that looks like. So we're gonna do a 35-second shot here. All right, and we're gonna get out of our low light mode and jump back into our stack. The last thing in the stack was our Andromeda shot, which you'll see. That's beautiful. The next one coming in will remove it. These are saved up on the server, skytourlive.org. You can go check it out. And we are still working on our application. The application is, I've got to work out with the AppSheet people how we can get that deployed to everybody. But once we do, it'll be great. Hey, Tim F. Nice to see you, and thank you for the Thanksgiving wishes. Greg O'Brien says, I love showing Saturn to people for the first time. Yeah, you know what? Saturn is beautiful, Greg. And this telescope is a wide field system. So as a wide field system, Saturn is a tiny little dot. All right. But the new system is an 11-inch Celestron telescope, and it's got excellent resolution. And we're going to be able to see Saturn a lot bigger, and we'll be able to see the cloud bands on Jupiter very easily, detail on the surface of Mars. Okay, and so we're actually going to be looking at that. You know, hey, old school. We're going to be looking at that quite extensively. All right, now let's do this. Let me just quickly process, a rough process. Already you can see the dust. Look at the color. See that? It's a brown dust that's in the universe. It's here. It's all over here. This is, again, remnants from supernovae explosions. Now, let me do the color correction again, and it makes it stand out even more. And now what I'll do is I will take our dark level and make the space blacker, and make the dust, and keep the dust a little bit lighter, so it makes contrast. Now you can actually see. Look at this. Look at this. This again is called the iris, and I can spell it out right there. You see it says Iris Nebula. All right, and we will set the target name. All right, and we'll save with annotations as well. So that picture will be available to you as well. Yeah, so the iris, okay, and we really do need to wait for a few more images to come in, but I can drop this down to kind of soften some of the noise. Then I can jump in here and show you this. Check this out. Look at this. Here's the star in the middle, and the star is, obviously its light is heading out in all directions. And what's happening is the dust in these clouds really, really likes the blue light of the stars. When the light hits the dust particles, they absorb it and reflect it out immediately, giving rise to the name of this type of nebula, a reflection nebula. Okay? And it's actually a scattering process that causes it to happen. The blue light is being scattered in all directions. The same process you're looking at right there on this screen is the same reason the sky is blue, because the molecules in our atmosphere are doing the same thing to the blue light of the sun. So when you see the blue sky, you're actually seeing the blue part of the sun's spectrum, which is red, orange, yellow, green, blue, indigo, and violet. You're seeing the blue light sent out in all directions. You're actually watching this scattering process, and there's a name for it. It's called Rayleigh scattering. But who cares? You know that the blue light is scattered light. And we see here that happens in space too. There's a lot of universal concepts that apply. And one of them is that small dust particles, molecules in our atmosphere, all right, as well, will scatter the blue light. And that's what we're seeing here. Pretty cool. So we'll let this come in a little bit, and as it does, you'll notice that there's an interesting development happening right here. Okay, this right here, you'll see this is a hole. This is a true void in the dust. And you can see through it and see the stars behind it. So you're seeing through the little hole, and it's, see my eye right there? You're looking at the stars back here through a little hole in this nebula. And that's what we're talking about. It's like a little keyhole. Okay. Look at that. See, as we do more, the nebula starts to really become defined well. We see a much better definition of the nebula. The iris is one of my favorite nebulae because it showcases, this is a better shot, it showcases the dark dust in our universe. Now you might say, well, what is that dark dust made of? That dark dust is made of carbon, silicon, and a whole host of other atoms that were created in supernovae explosions. But mostly it's carbon and silicon dust, carbon molecules that are very dark that make up a lot of this. This is planet building material, guys. This is the stuff that planets are built from. And I for those of you that heard the song at the beginning, you know, I write and compose a lot of music that, at the beginning of our streams. I've done all of it. And so one of the things about this carbon is that you usually find it in these dark, cold clouds. The temperature here is probably minus 215 Celsius. Minus 273 is absolute zero, and so it's just a little bit warmer than that. So maybe minus 250, minus 253 Celsius. So in those cold, dark clouds are these elements that are permanently locked up until such time as another star is formed, and it releases everything and makes a set of building blocks for planets, and then planets can form as well in there, and that's what we often see out there. So that's kind of cool. Okay, we've stacked 11. You can see right here. We stacked 11 images right here. And we stacked so that we can get rid of the noise. Well, the first one was really noisy, you saw, but now we can actually see that we actually have a much... I can make it a little brighter, and it won't be very noisy. It looks kind of nice now. And that's because we're adding up and averaging out all the noise. There's that hole I talked to you about. You can even see the highlights on the edge of the cloud from the star in here. And you can see the detail in here. If you want to see that detail even more, let me add one more bit of magic to this. Okay. And now you can see edges and very, very, very minute details in here. This is just spectacular. It really is very pretty. And we've done 12 images so far. Jose Navarro says the dynamic range from this star is nuts. Yeah, it is actually. If you look at our data here, right, the peak brightness is here, and it goes all the way down, to here, and when it starts getting messy like this, that's usually not very usable data. That's this noise that's still in here, and that noise gets less and less and less. We eventually have smooth curves, all right? And if I come down here and pick off less, it'll tend to make it a lot softer looking. See that? And now if we zoom in, that becomes usable for a while. And then at higher exposures, count, this will become usable as well, and we'll be able to really look at the very faint stuff in there too. Right now, this is starting to barely come out, but once we get more frames, then we won't have a whole lot of noise, and we can actually afford to do this to it and really pull it up, and then we'll see a lot more detail in there. But right now, this right here, this puts us at the spot where we can now look inside this nebula and look at all this detail in here. There's so much stuff going on in here. It's absolutely incredible. And amazing to think that you can't see that without a telescope. All this magic is lost unless you use a telescope. And a pretty darn good one at that. So I'm going to do this like this. I will pull the dark up the hill, so to speak, until we get right near the peak. Okay. And then we can pull that down. See, so this is really cool. The Iris Nebula, folks. If you join our Patreon, people in the moderate tiers of the Patreon will get several really, really polished, finished images for free as part of their Patreon. And we're working out what else to get you if you join our Patreon. We're thinking a mug with something like one of these on it or something. Not necessarily this one, but something that you might like. Very cool. And now it's very obvious, right? You can see all these beautiful stars, the clouds blocking the stars, a hole. You can see the stars through, more cloud blocking the stars, and then those stars again. These stars and those stars there are at the same distance from each other. They're in the background, and this cloud is inserted in front of it. Really cool. Pretty cool, pretty cool. I'm very much liking it. Cosmic Ray's here. Hi, Cosmic Ray. Cosmic Ray is a big fan of the Sea Star. They just came out with another one. I mean, I think it's great, but it is something. Yeah, Cosmic Ray, we imaged the supernova last time, actually, in 2146. It was magnitude 16 at the time, but we saw it quite obviously. It was very nice. C&D boy, what's happening? I just did my second round of pre-interviews for the Proof Is Out There show on history, and they gave me like 11 stories for different episodes. So C&D boy's gonna see me again. I mean, that's how people seem to know me, is from that show. Well, that's okay, you know. Part of it is I can't be bought either. If people say, we want you to say it's a UFO, but it's not. We want you to say it is. No. I have not relented on that. So far, no one's given me any trouble. Hey, Goblin, what's happening? Alright. Okay, we've done 22 images so far. That's looking really nice. See, it's getting sharper and more detailed up in here. Look it up at all that. Oh, look at that. That's really something. Very convoluted, complex pattern in here. There's these billowing clouds. And this billowing cloud, you can see it's lighter on the edge and denser in the middle. So the light dust passes through a little more light, and so it looks lighter. There's some that's over right near the star that's actually kind of dense, and it's keeping the star from showing through directly. Yeah, but you notice that it gives way to browns, and those browns are the color of the of the dust. The blue is the scattered light. Yeah, I'm not a Viewcast member. That's right. Actually, the network is recasting them because they don't like how toxic they are. I mean, they are toxic. They're just too toxic. Wow, this is something. This is really pretty. Hey, Uberku, how are you? Alright, we'll let this percolate a little more. 26 images. Let's go see. Where is this guy? Yeah, he's just getting to the point where you should be able to see him, Ray. 2146, the galaxy that has the supernova in it, is just getting to the point where we can see it. I was waiting for it to rotate around as we rotate on the Earth. Let me save this at 27 anyway. Save directly as scene. Okay. Then let's annotate. And there we are. So we're annotating right there. And what we'll do is we'll save this image with the annotations again. It's a second save of the same thing. Alright, that's good. That's really pretty. Alright, we'll go to 30 on this. The other night when I just shot for myself, I think I did the iris. I went to 100 exposures. And all of this in here looks absolutely smooth when you get rid of a lot of this noise. So that's just beautiful. So let me see if I can simulate what that looked like. It probably looked on the order of like this, but brighter. But look how beautiful that is. You can see all this detail in here, and that's with just, almost 30 shots. Hey, Greg O'Brien again, man, I love it. Have you ever been affiliated with the CIA in any capacity? Rumor on the street. No, I've actually, I do work for the Navy, actually, and I've done special projects for the Navy for decades now, mostly in the engineering model making business of designing new submarines. But I do that from my house. I work out of my home. Now and then I have to go to Washington for meetings and stuff like that, but that hasn't happened for a very long time, and I'm okay with that because that's 6 hours down and back. I don't fly. I typically drive down and back in the same day. All right. But yeah, I've never worked for the Central Intelligence Agency. I've worked for the Joint Counterterrorism Task Force and the FBI and NCIS. I've worked with them as a consultant, but I've not ever done anything with the CIA. Wait, that's a lie. I did work in Washington for one summer, and I did have to brief the CIA director. And we drew straws because no one wanted to drive all the way out to Langley. Okay, well, I lost. So I had to drive to Langley, go through all the hoops, and get all the clearance checks, all that crap, before I could walk across that floor. Okay. And they really do have what you see in the shows. They show it. Well, that's filmed there. They get permission. But yes, and I mostly these days I haven't done any of that kind of work in quite a few years by choice, and I will usually do work for the Navy still because, in fact, I'm working on projects with them right now, and new concepts in submarine technology. Something about it, submarines, inner space, underwater, and outer space like this. This is where I live. Here, not so much. Ray asked if we got snow. Didn't get snow. I had a dusting that disappeared by the evening the other day, but none now. It was all just rain here. James Hyatt, what's going on? Nice to see you, man. Very nice. Okay. One more here. Do one more and then we'll go to the supernova galaxy. The problem is, like I said, it's just south of the North Pole and we have to let it rotate up, and it's just about level, so it might be just visible right now. We'll try it. If not, there's plenty of other things we can look at up in the far north. Yeah, James is getting ready for Thanksgiving. Yeah, me too. Me too. Tomorrow will be a fun day. Long day, but fun day. Okay, 35. Let's save it. And now let's back out and let's do some processing to see just what we got. I'm going to overprocess now just to catch a glimpse of what else might be in here. Well, there you see it. Lots of dust in here. Lots of dust. There's a particularly dark object over here that actually is another dark cloud. And if it was in the view, you would have seen it. Not bad. This looks pretty good. And let's do this. Okay, and now we can bring it back to normal processing. And then go like this. Pull in a little more detail. There we go. Alright, and then we'll save it. And save exactly as seen. Excellent. Well, there's the Iris Nebula. It's just a dust cloud that's illuminated by a star, basically. And that's really fascinating. And now back to our low light mode so we can kind of like a little finder scope for us. Here we are. Alright. Now let's go see. Alright, this is close. This is close. Well, let's go see. Alright, so you watch the telescope's gonna move from here to there. There it goes. It rotates around. Yeah, let's make sure that, yeah. Yeah, we might barely be catching the edge of the building there. I'm not sure, but there's the galaxy anyway. We can confirm that by doing this. Solving for our location. There it is, NGC 2046. Okay, and we're going to center it in the view. Hey there, Marco. Daryl's not here tonight. He's got some Thanksgiving things to do. So I decided to go. It was kind of a last minute thing. I just decided to, why not, you know? Okay. Last time we looked at this galaxy, there was a supernova in this galaxy. And let's check to see if it has changed. We'll do a 25-second shot of the galaxy, and this first shot may not be. I might have to start that again, but only because I had to move it briefly. It's okay, it won't actually keep it if it's not well aligned. Okay, that's the overblown one. There's the galaxy. Let's get rid of this. And that brings us to this. This is the first shot. And you'll see that our curves and where we're picking off the curves is way wrong. We want this to be just to the left of the peak. And this to be right about there. So what I'll do is I'll just drag this and move it over to here. Okay. And then I will color correct to get rid of the blue cast on the sky. There we go. And now if we zoom in, we won't see anything yet. It was right here, right? This one of these. So you see a star here, and then there was something there. And I don't quite remember where it was. We'll have to see. Might still be there. I'm sure that Cosmic Ray will make a mention of it. All right. I may have to refocus because I swapped over. I recall the supernova, there were two stars in here, and then there was one like this one. Maybe it was the supernova. Is that true or not? I don't recall. Let me bring this in here. See, we've got too few stacks here. We got to stack more. Well, either way, I'm going to save it so we can always do a comparison later. Thank you, Michael Hedrick. I will look into that as well. But I can see that I will have to refocus first. So I'm going to get out of this for now and go into my low light mode and do a focus run. Now it doesn't matter how much I'm zoomed in, it's still looking at the full frame for the focus. And that'll help us see these faint stars better. Okay, so let's do that. right, Sam S. Thank you. I'm going to keep trying here. I think there's a conversation going on in chat about total destruction. Okay, Greg O'Brien and Stan are talking about something. Oh, Greg O'Brien's in DC as well. Okay. Or Maryland. Or Virginia. They're all right near each other. You can see our curve being built here, and this will start coming up as it goes out of focus more. And then it'll find a center point right about here. Probably within a 2 or 3 seconds or so, we'll see a line show up there. There it is. And it makes the curve, and there its focus position. Now, it's still going to 12 samples, so this number will change ever so slightly as it does that. And then once it's done focusing, then once it finds the best focus, it automatically starts refocusing, and so it's done so. And now our focus is right on the money. So I can get out of this. And now we can start our exposures again. We'll do a 25-second shot. Like this. And off we go. Our previous live stack is going to just be cleared because we don't need it. Yeah, Ray, isn't the supernova, is it this guy right here? Or was it inboard somewhere in here? I mean, I know this one wasn't it. I don't think that one was it. Was it this third one in the galaxy that was actually the supernova? Ray will respond, I'm sure. Okay, let's bring this down to kind of get rid of some of the noise. Yeah, okay, so I'm gonna put a little marker around this object because I want you to see the object that's the supernova is right here. It's inside that red square. Of course, that doesn't really help much, does it? Because I gotta really make sure that I show you just a tiniest bit of a object here. So that guy right inside, that's the supernova in there. Okay. So as we expose a little more, you'll see that little dot in there will increase. In brightness. This dark lane in the galaxy that Ray's is talking about, it's kind of odd because it looks like it's on a weird angle. And so I have to check this galaxy in Sinbad or something to actually see what's really going on. It's not the only galaxy in the image though, because we've got one up here too. And so let's go look at that. So I'm going to raise my... Okay, so this is... Let me calculate more correctly. This is NGC 2146A galaxy. It's a magnitude 12 galaxy. This is a magnitude 10.6. The bigger the number, the fainter it is. The moon is minus 12.6 or so. Vega, the brightest star in the summer sky, is a star that is an A0 star, and it's a 0.0 brightness. And let's look at the night sky, by the way. Oh, we got some contrails. Right now, we are looking up in, we're kind of up in the eastern side of things. Okay, the North Star is up here, we're kind of up here. I'll be replacing the lens in this camera with one that shows the entire bottom and top as well. Right now we don't get the full view, but it's stunning. It looks beautiful anyway. And I'm going to be building a second all-sky cam for Benson. Okay, so let's color correct this one more time. There we go. Drop this down. Kind of soften the noise. That really shows it very well. Yeah, it's a barred spiral, as Ray says. But it's a tortured barred spiral. There's some odd interactions going on with it. Possibly with some other galaxy. Not sure. Is this the supernova here? Or is this the supernova? I'm beginning to think it's this one here inboard. So 2146. Interesting, because this galaxy you're looking at, its distance is 127 million light years away. So the light we're seeing, this supernova occurred 127 million years ago. Okay, and specifically for Greg O'Brien, think about what was happening on Earth 127 million years ago. That's when this supernova actually occurred. The light from it was 127 million years from showing up here. And that light, when it was first created, we had dinosaurs roaming the Earth. In fact, we were in a different period altogether from the period in which the dinosaurs died. So they died in the Cretaceous Tertiary boundary. And here we're looking at 127 million years ago. You look up in your chronology, geologic chronology, and find out what period that was. And you will find that while those dinosaurs were blissfully roaming the Earth at that point, and the oceans were teeming with ever-increasing life at that point, you'll find that at that very moment, a star exploded in a galaxy far, far away. And if there was another planet near there that had life, well, then it's possible that that life may have been extinguished by that supernova. So we are indeed looking at a time machine, as Greg O'Brien just said. I think this is the supernova. I don't think this is the supernova. The cosmic ray, please confirm. Because I seem to recall that this was the one we're looking at. So that said, I'm really excited about the new telescope because we'll be able to look at things like this with these are small objects. We'll be able to look at them with different eyes, and it'll be much better. Well, I mean, large-scale objects is what this telescope's for. Large, expansive nebulae, things like that. The next telescope, we're going to have narrowband filters on it, a spectral imager, and we'll be able to see the spectra of the stars, which is really cool. I also have a spectrometer behind me that I want to see if I can put on that telescope. So we could, for instance, get the spectrum of the supernova and see what elements are being given off and caused to glow by the supernova. Jay Kelly says it's the middle star, meaning this one right here. This is the one I mistakenly thought was it, but I think this is the one. I believe that's the supernova right there where my arrow key is. Let me know. I'm pretty sure it is. Thank you, Greg, for that compliment. I'm very happy to yeah. Oh, the one I mistakenly thought, so it's this one here? This is the supernova? See, I thought it's one of these two. And I thought this was the one. But now I'm thinking this may have been the one because we had these two, and then I couldn't remember if it was this one or that one. So Jay Kelly just put in there, is it the left one or the right one? He answers yes. Well, there's a delay a little bit, so I don't know. Just say it's the left one or the right one. I'll know what you mean. Left is this one, right is that one. Right one. Okay, so it is this one. All right. I couldn't remember. I mean, we took it the other day, and it looks about the same. It was about 16th magnitude back then. No, this is all stacked fantasy. We've got 23 images in the stack so far right there. See? It says 23 right there. 24 now. So we have 24 images stacked right now. And this is the supernova, as it turns out. Couldn't remember which one it was. Oh no, what are you talking about? It's fantasy, not a problem. You don't know what all this stuff is on the screen typically. You just want to see the pretty pictures like most people, and I'm okay with that. You know, if I'm unclear, that's my doing. That's my fault. So let's try a process here and see what it wants to do. Yeah, it's going to make it really bright. Actually, this is helpful because if you notice, all the stars, they have different colors. Notice this star? What's the color? You notice? It's actually a little bit blue, isn't it? And this blue color is the result of high heat from high frequency light. The high frequency comes from extreme temperatures. And when a supernova explodes, it's going to be blue at first and then tapers down to orange until finally it fades away. And so we're seeing a high temperature object right here. And it's 127 million light years away. Isn't that crazy? Goblin, I thought I was the only one who came here for pretty pictures. No. Guess what? Little secret. I do too. Yeah. I may know the science of these things, but let me tell you, I've never ever shaken the fact that the universe is the most beautiful thing that's basically hiding in plain sight over our heads. I think that's really cool. Okay, let me drop this down now. Yeah, definitely got a nice blue there. Let's see if we can zoom in a little more. We'll zoom in way too much. Yeah, there's definitely a blue cast to this. Let me color correct. Yeah, this has a blue cast to it. Nice. You see the disk of the galaxy is blue because it has young hot stars. The older stars are in the middle of the galaxy. They correspond to our population 2 stars, which are the older, redder stars that we have in our galaxy. And the blue, hotter stars in our galaxy are the population 1 stars. And they usually are formed with lots of additional elements in their atmospheres. Keep in mind how how things work. Okay, I'll get to that in a second. Ray says his Firefox croaked on him. Yeah. Okay, but you got this blue here. This is the blue of the supernova. Now, here's how a star works, okay? In the star, you have a core. The core is the only thing that's doing fusion. It's the only area where, in the beginning stages of star's existence, where hydrogen is made into helium. It's the only place. It's not in the whole outer body of the star. People think that the star is doing everything everywhere. It's not. The star's center core is a little less than 20% of the size of a typical star. Okay? So that means that fusion is going on inside that tiny area. The hottest part of the star is in the core. All the rest of that stuff that's glowing, that's just plasma, meaning it's atoms that have been heated so high in temperature that their electrons are stripped from them, and they're literally protons all running around atomic nuclei. Okay, running around with loose electrons. And some of them get loose and leave the star as solar wind, or as stellar wind. So, when we look at a star, only a small percentage of the star is actually the core. So, whenever we talk about a star going supernova, it's the core that's destroying itself. It's not the outer envelope. The outer envelope is just along for the ride. And it's in that outer envelope where all the elements that the star was made with reside. So if we do a spectrum of a star, we don't see what's in the core. We see what's in the envelope of the star. We see what's in the whole rest of the star. And we'll see, like in our sun, we'll see calcium and magnesium, phosphorus, we'll see oxygen, we'll see carbon, we'll see neon, we'll see all these different elements in the spectrum. And the sun can't make those elements, all right? The sun is made with those elements. So that's why the sun has them as floating around in that outer envelope out of the core. The sun can make hydrogen into helium, yes. The sun may make helium into some carbon, yes. Beyond that, no, it's not massive enough to get the temperatures high enough in that small 20% core to start making the next level of fusion, making carbon into oxygen, and oxygen further on down into magnesium and iron. You need a much more massive star to do that, and higher temperatures in the core, hundreds and hundreds of millions of degrees Celsius in order to do that. And that's something that our sun can't do. So if a star goes supernova, it guarantees that it means that the star is many times the mass of our own. So when we see this star like this making a supernova cloud, a debris cloud, we know that this happened 127 million years ago, and it was a hot blue star that blew up. At least it started as a hot blue star. When it blew up, it was a red supergiant. Okay, and it's really, stellar evolution is somewhat complex and can be considered complex. I seem to have vanished. So I don't know how much of that I really want to talk about right now. I don't know if that's the best thing. There we are. I'm back. Okay. And now I'm gone again. I know why. Yeah, that's why. All right. Okay. All right. So, we have 40 shots here. We're going to save it right here. And I'm going to actually leave it like that, and I'll relabel it as supernova. And this is the supernova once again. I think I did this, but I'm going to save it with annotations one more time. Okay, very nice. Ray, thank you for that suggestion. That was a great idea to go and look at 2146 again. Okay. All right, let's back out of the zoomed in feature here. All right. Okay, let's go to this guy here. And let's check out, let's see if we can look here. We can't do the Heart Nebula now, because Heart Nebula is down here. I thought, let me, it's down there. Or no, it's over here. Hold on. I might be able to do it. That's Flaming Star. We don't want to see that. It's going to be right about here. Because that's something else. That's really pretty. Let me see if we can do that. Yeah, we can do it. We're going to do that. The Heart Nebula is really pretty. This is going to be our feature object for tonight because it's just gorgeous. In the same area of the sky, you'll watch the telescope going to move just a little bit to the right. But it's higher in the sky, so that's kind of cool. See, right there. Yeah, all right. Looks like a cluster, right? It sure does. But there's more than meets the eye here, as you'll see in just a minute. Okay. So we're going to move over a little bit now, because there's another cluster in the middle of it all. This is a stellar nursery, and it's got so many cool features in it that you could stare at this for hours. And Medusa Nebula is another possibility, Ray. Thank you. All right, let's do this. Now, there's two ways to go, because up here is the Fishhead Nebula. Okay, it's right here. But we also have a lot of stuff down below here. So I'm going to go down here first and spend time down here looking at this. That's too far. I don't want to go all that far down. I'll kind of center it a little bit. This is good. Okay, this is... You're going to find something interesting here. This is a hot young cluster of stars. And this cluster, with its energy of stellar winds, has cleared a path around it. Just like a bulldozer, these hot young stars' radiation has cleared a path. And you'll see it. And we do a 25-second shot here. All right. And there we go. And it's really a very, very cool location, as you'll see. Let's do this. Okay, let's go into our stack and go into our our deep sky mode. Deep sky mode. All right, and we'll see this image. Now, this is just scratching the surface because we're gonna do a color correction first. And now watch how much detail just pops when I do this. Bam! Check that out. This is an amazing stellar nursery. We're gonna start moving our curves around here, and you're gonna see this beautiful nebula start to take shape here. It's a big nebula, and up here is another nebula called the Fish Head. And I'm just doing this central core here of the Heart Nebula. Here's the heart. See the heart? Ta-da! Yeah. Yeah. Jay Kelly says your setup is really picking up the color. I actually changed the color response just recently, actually 2 days ago, and I've been dying to show everybody how it looks now. The colors are much more vibrant and much more realistic, actually much more of the real colors. Oxygen 3, for instance, is ionized oxygen atom, and it's what's called a forbidden line. You can't get that to happen here on the Earth. You need hot temperatures in a rarefied gas. That is a gas that's very low density. So a nebula is very low density. All right. We might have 10 to the 20 atoms in a cubic centimeter. That is to say, a sugar cube size of air here on the Earth. Okay, in a nebula, you have about 30 atoms in a sugar cube size, and that's considered reasonably dense. You can have 30,000 atoms, right? But that's still nowhere near 10 to the 20th atoms. So obviously, the density plays a role in what the atoms can be ionized to. And oxygen 3 means doubly ionized oxygen. So why isn't it called oxygen 2? Because oxygen 1, this is Roman numeral 1, Roman numeral 2, Roman numeral 3. So I. Okay. Oxygen 1, or oxygen with the I after it, the Roman numeral 1, that's the base state of oxygen. That's the state of oxygen when it has all its electrons. Okay. So the 1 is taken up. So if you ionize it once, that becomes oxygen 2, ionized state 2. And if you ionize it again, meaning another electron is ionized, that becomes O3, or oxygen 3, the third ionized state of oxygen. And what happens is the electrons get bounced off the atom temporarily. They collide with other things out there, dropping back into the atom, and as they do, they absorb energy to leave. And when they come back into the atom, they give off energy. Well, the nature of the transitions that the electrons make, they absorb electromagnetic energy, that is light energy, as they leave the atom, and they give off electromagnetic energy, or light, when they go back into the atom. In the oxygen case, the O3 transitions, the electrons dropping to certain positions, that color is teal. It's like a teal blue color. It's the most beautiful color in the universe. It looks very different from a reflection nebula like the iris we looked at. The iris looks like a pale blue, or a beautiful cobalt blue in some cases. But what happens with the teal color is that's the actual color of the transition of two electrons back down in to the atom, giving off two different kinds of light, which add up to looking teal to your eye. And there's other transitions they're making. There's other things that the oxygen atoms are shooting out for color, but the teal is the dominant one in this low density region of nebula like this. So teal, that beautiful teal color, which is now going to be in many of our images now, it's just so stunning. That color is when oxygen is present. Here, mostly hydrogen is present. So what we see here is red transitions. And when the hydrogen electron is bounced off the atom because it absorbs a lot of energy, generally ultraviolet energy that would come from these stars, these hot young stars in the cluster, well, they would also then give off that energy when they bounce back into the atom. As they cascade back into the atom, they go down to a particular level. Most of them go to the second level called N, as in November. N equals 2, the number 2. That second level is where the hydrogen alpha transition, or the red light transition, is. And most of the electrons will go to that level. All right, and so the dominant transition is the hydrogen alpha transition, which means red light coming from a nebula. So the colors of the universe generally are red for hydrogen emission, as you can see here. Teal for oxygen 3. Blue for scattered light or reflected light off of these nebulae, dust clouds. Okay. And various other colors that signify different element transitions that you might see. But generally, you'll see a lot of hydrogen and you'll see a lot of oxygen coloring in the starlight, in the nebula colors. And that's because hydrogen is the most dominant, the most plentiful element in the whole universe. Next comes helium, because hydrogen makes helium in the fusion process. Then the third most abundant element in the entire universe, believe it or not, is oxygen. So that teal color you might expect to see a lot of, and we do. All right. So hydrogen we see the most of because it's the most dominant. All right. And then the third most dominant is oxygen, and we see a lot of that too. All right. And interestingly, the fourth most abundant element in the universe is carbon. And where is carbon? Well, carbon is right here in all this dust. All the dust clouds. So we're literally looking at the building blocks of life right here in front of you, right in front of your eyes. You're seeing the building blocks of life right here. This is right here. This is all the building blocks of life in here. This dark cloud right here, this is a building block of life right here. That's got a lot of carbon in it. And carbon is what you're made of. And carbon is what the universe is based on when it comes to life. I'm a carbon bigot, I admit it. Okay, I believe life is based on carbon almost exclusively. Because if you look in the periodic table, right below carbon is silicon, and people say, and there's silicon in these clouds, no doubt. There's silicon in these clouds, it's in here with the carbon. But the silicon has a problem. The silicon is a very robust element, and what happens is when the silicon makes a bond with something, it doesn't like to let go. So that means that silicon bonds are very, very tough to break apart. But organic life requires the ability to break apart bonds and make new ones readily all the time. Right now in your bodies, thousands of bonds are being made and broken as we speak. Okay? Because the carbon atom, with its 4 electrons on the outside of the atom, can bond and break bonds with all kinds of things. More things than any other element in the entire periodic table. We call it the granddaddy of all elements, actually. So, carbon is being the most, as the most flexible atom in the entire periodic table, is also very understandably the progenitor of life. It's what life is based on because of the flexibility this atom has. Silicon doesn't have that flexibility. And the most likely element that could host life is right below carbon in that column. Those are the atoms that are most like each other in elements. So, that said, the next most likely one is silicon, and it's not very likely. Silicon tends to make crystal bonds. You've seen them, you know it, because every time you walk on the beach, you're walking on mostly gas. Did you know that? When you are on the beach, you're walking on silicon dioxide. A silicon atom with 2 oxygen atoms attached. So 2 out of 3 of the atoms are gas. Oxygen. Isn't that crazy? You can actually, you can use that if you want. Yep. Ray, are you talking But yes, we're going to use PhD2, which is going to guide on the new telescope. We have an off-axis guiding system. We have the off-axis guider camera. I've adjusted the mirror into the field. It's going to sit ahead of our filter wheel, and it's going to be in front of our 294 MC Pro that we have now. That camera, and if that camera is sufficient, then we'll continue to use it. It's actually tuned for this telescope. The 294 MC Pro is tuned for the Celestron 11 quite nicely. J. Kelly says, can you tell me what scope and camera? Okay, that's what Ray answered. Yeah, it's a 10-inch LX600 Meade that we've modified from the f10 focal ratio down to f1.8. All right, it's not f2.8, and we're using a ZWO 183 MC Pro camera on it, because that camera is tuned right to this particular arc seconds per pixel. We get the best arc seconds per pixel result with that particular camera and sensor and size of the in microns of the pixels basically in the camera. Is elemental carbon out there or carbon combinations? Both, Ray. Both, Ray. In fact, when you look at stuff like this right here, okay, this stuff here, let me zoom in on this because this is helpful. Okay, let me come over here. Okay, see this dark nebula in here? Okay, a lot of this is carbon-carbon compounds, where 3 out of 4 of those electrons are on the outside of the carbon atom are shared with another carbon atom. And it's a really solid carbon-carbon molecule. And the temperature in these clouds, deep in the clouds where it's darkest, is probably minus 258 Celsius. Minus 273 is absolute zero. Okay, Celsius. So we're talking about just a few degrees above absolute zero in this cloud. But if a star forms in here, then these little dust particles in here, which also now are coated with liberal amounts of different types of ice, ammonia, methane, carbon dioxide, water ice, etc. Okay, formaldehyde, and methanol. I mean, that's gonna melt and form a slurry of material that can be used for planet building. And they also have other elements in there of all kinds, calcium and phosphorus and all kinds of supernova remnant material is in here as well. These are literally the building blocks of life. And as I might have told you all before, when you look at this image, it's stunning. I might have told you before, when you look at something like this, and you look in the dark, this is where life begins. Okay, I did write one of the songs that talks about life began in the dark, and that'll be one of the startup songs at some point. But it definitely shows that it definitely tells you what's going on out in the universe when we look at these. Now, here are the stars. I got to point this out. Here are the hot young stars. And they're spewing this really, really heavy-duty radiation. And as they do, what's happening is they're sending this radiation out in all directions. And so what they do is they actually will erode some of this area away. A lot of this material is getting eroded away by the energy being thrown out by these very, very hot stars. That's happening in here too, but it's happening over time. And so the way this looks now isn't how it's going to look in a million years. It's going to look very, very different from this. This might all be gone. But you'll notice also that we're seeing some of this dark dust is remaining behind, and a lot of the hydrogen gas that was in here has now been pushed away. That's kind of what's happening here, is we're watching the work of the hot stars' stellar winds that are pushing this hydrogen gas away from this region. All right, and that's what happens in these regions. These stars do this. We look at the Rosette. The Rosette Nebula has a beautiful hot cluster in the middle, and then it's an open cavity all the way around It's very, very nicely made. It's a very nice spherical cavity. And then you see a nebula around the outside. That's because the stars cleared that cavity with their stellar winds. See, if you're not careful, you're going to learn something when you come here, guys. All right, let's see if we can bring out some more detail in this dark material right here. Oh, look at that, guys. Look at that. Let's zoom out and check out the whole image. Okay, you can see the heart right there. Heart, bottom of the heart. There it is. Look at that. The heart nebula. Fish head is up out of the view. The rest of the heart is here. It actually kind of stops just after this, so we're actually catching most of it. Let's color correct one more time. Good. Move our curves a little bit. There we are. Look at that. Now, if we zoom in, all right, you can start to see even more detail going on in here. Look at the detail in here. Now, these little tiny, look like gossamer tendrils. You know, they're a fraction of a light year across each. You know that? The tiniest ones you see, that's like a fraction of a light year across. You know, and this is several light years long. There is a thought process to go with that maybe our sun is inside of a dark nebula to some extent. And that maybe the dark nebula that we're in is hinted at by none other than the Pleiades. Because the Pleiades are lighting up dust around them and doing that scattering process to make blue nebulae around their stars. And the Pleiades are a couple hundred light years away. So given that they're relatively close, I'm going to say that possibly we may be in that same dark dust cloud. Because as I said, they're light years long. They're many light years long. And they're very extensive, so it's possible that we are. But we're inside the forest. We can't see the trees, can we? That's kind of how it is. But there's our heart nebula. Look at that. This is just beautiful. Wow, look at that. Okay, so we'll go to 40 images. Remember, SkyTourLive.org is where you'll find this image when we're ready, when we save it. And then I'll save it now and then I'll save it again. And then you'll actually find that we will on the server you'll find the one that has the annotations on it as well. And I'll show you what that will look like, and I'll save it one more time anyway. So let's bring this up. Okay, here's the Heart Nebula. Alright. And then we'll save with annotations. And that's going to be out there as well. Okay. And we'll save exactly a scene. I think I did this. Yeah, I think I did. Okay. Oh, man. Yeah, the color is so much richer now. I'm just so pleased. Let's go way in here. Look at that. Wow. That's just an immense structure of dark nebula in there. And of course, faint stars, even ever so fainter. Now, it's those very faint stars you might look at and you'll say, any one of those could be like the sun. Any one of those faint stars could have planets around it. Any one of those faint stars could be having life coming out right now. Coming up. So not bad. You know? Yeah. Goblin says the darker red is beautiful. Yeah. And this is actually more natural red, so our colors are going to be more natural from now on. And this is astonishingly good. Okay, let's just save it now and save it exactly as seen. Very nice. Okay. And that's our Heart Nebula, except that I didn't label it the Heart Nebula. Okay. I'm gonna do this. I'm going to change the name here. I was supposed to do that. Okay. Now the target name is set. And I'll say yes. Yeah, I know. Okay, so now we can save it again. Alright, now it's going to be in the Heart Nebula folder. And save exactly as seen. And where is that folder? You can find it at skytourlive.org. You go there, and as you scroll down, there'll be a section that says, I want to see cool pictures or something like that, and it'll show you exactly what to do to go to our server directly yourself and sift through 2 years of pictures. And the latest directory will be all of these pictures. Okay. So that said, let's now get out of here. Go into our low light mode. Yeah, we are. Now, in our low light mode, let's see if we can... Let's see if we can do another really cool object that I think people will love to see. I know you'll love to see this one. Okay, this is the double cluster, the famous double cluster. And it's an interesting cluster of stars. Alright, and I will be bringing us over just a little more, because I told it to go to the leftmost one, and we're going to actually go to the center them up. This is a glittering jewel box in the sky. It is so beautiful. You can see it with your naked eye. Yes, that was meant to rhyme. The double cluster is just off the end of the tip of Cassiopeia on the way to Perseus. And it's 2 young clusters of stars that actually have been, they maintain themselves gravitationally for quite a while, and so they've actually evolved, and many of the stars in here are now red giant stars. They've gone through their first stage of helium burning, or hydrogen burning, and making it to helium, and then they are starting down the path to fuse helium into carbon. Okay, and so where is this cluster? This cluster is right there, and here is the W of Cassiopeia. Off that last star in the W, you draw a line between that and the brightest star down here, and that's Perseus, and it's about halfway in between, and you have the double cluster, and you'll see it as a fuzzy object in your night sky. So let's do a 15-second shot of this. 15,000 milliseconds is 15 seconds. Okay, so we're going to come out of that, go into our live stack, and this is the previous object, which will auto clear the Heart Nebula. That's really beautiful. Wow. And the first thing you'll notice is there's red stars in this image with the double cluster. All right, let's color correct it and do some processing, because we're way past our peak here. Let's bring that all to the left. Okay. All right, and now you'll see that we have a red giant. We have a red supergiant there. We have this guy and this guy and that guy, this guy. These are all the red giants in this cluster. They are part of this cluster. Now, here's how these things are situated in space. Okay, now first things first, let me do this. I'll drop this down a little bit. Okay. So this cluster here, you'll notice one's a little bigger than the other. This one's a little smaller. This one's closer to us. This one's further from us. So they're kind of like this in space. This is the dark, this is the small one, and this is the big one. And from the side, they're actually they're far from each other. They're a few tens of light years, maybe 100 light years, I have to remember exactly, from each other. But it could be a couple hundred light years actually, or more actually, from each other, if I recall. Several hundred light years away from each other. But they just happen to be along the same line of sight, so it looks like they're right next to each other on our flat-looking sky. But they're not. They're actually separate from each other. And if you look at this, you can't help but see how this one's smaller than this one here. So that's what you're seeing. Beautiful double cluster. Really pretty. Wow. Yeah. All right. So now what we'll do is we're gonna annotate this. There they are. Double cluster. Save image with annotations. And then we'll take one cluster and we'll say the target name is that. Yes. Okay. I'll come back here. We'll save it. Wow. So what you get is this. This is the image that we just took. And this image will be up on our server in, I'd say 30 seconds. And you'll be able to go find it in our directory, but you gotta read the instructions on how to get to it. In time, our application will be available that Izabela Melamed wrote, and we will be able to supply that to you as well. Okay, so we're gonna save this. Oh, okay, sorry, we had saved it already. All right. Okay. We'll do 12. Hey Lubo in China, how you doing? Yeah, Cosmic Ray, we had talked about defocusing in the past quite a lot, because that will allow you to see the colors. Yes. Okay, it's messing up, but this is good. This is actually really nice. Beautiful. So that'll be up there for you to see as well. And now in binoculars, you can expect to see something that looks like this. Maybe with even more detail than this. It's just beautiful. Yeah. Lubo says, got myself wider scope to piggyback 8HD and waiting for weather to improve so I can continue with imaging. I'm amazed how sharp it is. Yes, it's beautiful. Sharp star. Yeah, very nice. Nice. We'll look that up. Outstanding. Okay. Very good. Very, very good. Okay. Now let's go here and do another object that I think is just beautiful. shot this on Halloween. It's called the Gamma Cast Nebula. This little guy, I did it on Facebook too. You saw the post on Facebook maybe. And it's just a gorgeous nebula. And we're gonna try and shoot another one tonight. Might be. I'm looking for Navi. Let's see here. Let's see what we got in here. Yeah. Let's go here. Yeah. Gonna move over just a little bit. There's no name for it. It's sometimes called the Ghost Nebula. And we shot that, like I said, on Halloween. It was really nice. But this is the one we're looking at right here. Okay. And there's Navi right there. Okay. All right. Okay, this, we're going to do a 35-second shot here. All right. And let's do that. Okay, 35 seconds. We're going to go into our deep sky mode. All right. The last image we saw in here was of the double cluster. That's in our buffer. And that will go away. The buffer gets overwritten, but the image does not. That's been saved. Dean Boast the door. How you doing? Hey Kevin, good to see you. I missed you before. Sorry about that. Daryl's not with us tonight. He's working on his Thanksgiving prep. Here it is. Look at that beautiful. This is a reflection nebula here with this gorgeous ionized hydrogen region here mixed with dust. There's dust and all that through here. This is literally one of the arms of the Milky Way looking away from the center of our Milky Way, looking out further toward the edge of our Milky Way. That's where we're looking in this relative direction. Okay. Amazing. Now. Okay, we're going to... I've got to set my filter here. What's going on with the filter? Okay, only one worked, and I gotta figure out why. Okay, we will fix that. All right, let's do this. Let's make this 30. And we're going to do this. Try this again. Okay, you want this guy. So the target name. Whoops. Why did I do milliseconds? I didn't want that. Okay. One more time. Clear. Sure, Dean. Dean says thank you for the stream. Hey, it's a nice stream to do tonight, I think. Let me clear this so we can start at 0. So there's our ghost nebula, as I said. And let me make sure that we have our clear skies still. I think we have light clouds in here now. Yeah, we're going through some light clouds, but let's keep going. Give it a try. If the second shot doesn't align, then it's probably having trouble aligning. Okay, that worked. So, all right. There we go. So Navi is a very hot star, and it's ionizing hydrogen gas around it. And when you ionize a gas, it will glow, and that ionization glow for hydrogen is red. And this here is dark dust. This blue is not the teal blue. It's actually a regular cobalt or royal blue. That is a reflection nebula. That is to say, scattered dust, scattered blue light from this star is being picked up by these tiny pieces of dust and sent in all directions. Okay, well, we're still only getting 2 images here. Sometimes it just happens that way, and I don't know why. Oh, maybe I see why. I think this will take care of that. And to raise my filter tolerance a little bit. And then we should get a nice green bar there. Yeah, good. Alright, so this will be good for the rest of these. And you can take the Ghost Nebula as well as this Reflection Nebula later. Let's go back to our all sky for a minute. Here is Orion rising, see it? There is the belt of Orion. Here's the sword of Orion, which has the Orion Nebula in it. Here's the Hyades. That star there is Aldebaran. It's orange. Not part of this cluster. It's actually much closer. There's Jupiter. This is the Pleiades right there. And we are up in Cassiopeia, which if you turn this on here, you'll see that we are right here. Okay, and we are photographing. You see the W of Cassiopeia right here. Our camera is looking right here. This is Navi, or Gamma Cas. And so this is called the Gamma Cas Nebula that we're looking at. So that's what we're looking at right there. And that's that middle star. If we go to our star chart here for a sec, and we back out a little bit, you can see the star that we're looking at. There's that middle star right there. And the others in the W, and that's where we're looking. Very nice. Indeed. Okay, that's really cool. There's a lot of stars here. You gotta wonder, you look at these stars. Now again, they're all different distances from us. All different distances. But look at the detail on this cloud. Isn't that amazing? I mean, look at that little tiny star. That little tiny star that, unless I pointed it out to you, you might never have seen it. Maybe that little star has planets around it. And maybe there's life on those planets. We don't know. There's so many cases like this in the universe. So many cases. But I can tell you one thing. If that star is near this nebula, then you can be sure that Navi has probably sterilized any planets. Because the ultraviolet radiation is responsible for lighting up and causing this nebula to glow. And this nebula is light years from Navi. But ultraviolet energy from a hot star like this goes a long distance. So we're looking at the possibility that Navi may have a sterilization sphere around it where stars may not survive in there. But if this star is much further away, okay, for instance, or this star is much further away, that little tiny star right there, then who knows? Maybe they are beyond Navi's ionization potential, and it might be a bright star, brighter than Sirius in our sky to the people on the planet there, but it could be a potential life source, a life-bearing planet for all we know. I think life in the universe is the norm. It's the rule, not the exception. That's my feeling. Look at this. Let's stick around in this nebula. Check that out. Not bad, huh? And we can actually kind of make it even nicer looking by just dropping that a little bit. And we can also kick up and over-process it to see what's really hiding there. And now if we zoom out a little bit, you can see the extent of the Navi region. Look at all this. Gamma Cast Nebula, this is just one part, and this is just one part. It's all this too. Look at all this down here, all the way out and across and down. It's absolutely incredible. And so we can bring this in and exaggerate it this way. Okay. And I will bring this in just to the left of the peak, because that makes our space, the black part of space, as dark as it can be without losing data. That's incredible. And then we'll drop this over here. That's too far. But the comment was made about the dynamic range earlier, and what that means is when we look at this nebula, okay, let me back out a little. We look at this nebula, you can see subtle detail in there, and we can actually pump this up really high, okay, like this, so we can make it really, really bright, okay, so you can see what's around it, or we can come all the way down here and make it very dim so you can actually see the subtle detail inside. So there's a lot, and that's this distance here translates to a variety of different detail levels we can see, and that's called a dynamic range. So we have high dynamic range with this camera that we're using. It's really perfectly tuned to this telescope. Oh, that's pretty. By the way, in the intro song, you saw the SkyTour building we currently have, but then you also saw the buildings out in Benson that we're moving into, one of those, and the leftmost one is the one that we're moving into in that image. Right. These halos are an artifact of our system. It's pretty. Okay, 15 shots so far. I will take and save exactly as seen. And so this is the image you get when you go get it on the server. So you could zoom in on it and check out everything if you wish. For even more professionally processed images, you join our Patreon, and that will help us tremendously. You can also, if you wish to do a one-time donation, you can go to skytourlive.org and donate something to us if you like. We'd very much appreciate it, because we are trying to bring astronomy to the world and the masses. And you got to admit, it's cool as hell. There's no other astronomer doing this out there. None. Absolutely none. You know, there's people doing what I'm doing, okay, but they're just taking pictures of an object and spending hours doing it. And we're showing you multiple objects because we set up our telescope to be ultra fast. Hello, Lady Astrid. How are you? It is really pretty, Lady Astrid. It is pretty. Tim F wants a SkyTour shirt. Yeah, we got them. We got them. We got a lot of stuff. Go to SkyTour shop up there. See Etsy store here. Right there, SkyTour shop at the top left, top right, and check out 40 or 50 different products. Want a bedspread that has a gigantic nebula on it? We got it. You want boxer shorts that have a nebula on it? We got it. You want a bathing suit that has a horsehead nebula on it? We got it. Socks? We got it. Mugs? Yes. Water bottles? Sure. Shirts? Yep. Hats? Absolutely. So it's really cool. It's on Etsy, SkyTour shop. Okay. All right, 20 shots. I'm going to save it again. Very good. Let's check. I'm literally between cloud banks on this, just so you know. I know it doesn't look it right here, but there's two parallel cloud banks coming along, and I'm squeezing in this stream before cloud banks, but I can see we have a little bit of haze here, so we're getting some. And you see how the lights from distant Phoenix are showing out to like here? Yeah, it's showing that we have a very, very light cloud cover that's happening right now. That's part of that other front. But I had to do this. I had to get you guys a stream before we had Thanksgiving. So there we go. Lubo, this music is actually the YouTube music that you can get on the YouTube channel. I'm actually making lots of music and composing our own music to put in to use as our background music. I've got maybe 20 or 25 cuts made already, and I'll have more, and then we'll just put that in. Different types. Instrumentals for the most part, obviously. And with the lyrics, when you hear music with the lyrics, I write all the lyrics, so that stuff. I set up the instruments and which voices are going to be used to sing it, and it's an AI generated song. And sometimes I'll go through 20 or 30 different variants before I have the right one. This one is not my my music here, and these are not mine. These are just the YouTube ones that are standard royalty-free stuff. It's actually not bad, but I'm going to be replacing all of it with our own. So before long, all of it will be. And who knows, maybe we'll make a SkyTour album that people can get. That'd be kind of fun. Okay. 25. I'll save it. Very nice. Yeah, that's good. All right. Let's see now. Let's go back to our low light mode. Okay. Let's check this out now. Let me see if let me see where it's placed. Oh, it's set already. Dumbbell Nebula has set. Okay. That's okay. Then that means also that the veil has probably set as well. Yeah, it's low. Okay. It's way up in the northwest. That's okay. I'm alright with that. I'm going to do one more object, and let's try this. Let's see if it's available to us. Yeah, the helix is also setting. It's very low. So that's not good either. Alright, well then I know what I'm going to do. I'm going to do this one. It's the companion to the Heart Nebula. The Soul. And it's right nearby. So we'll go there and check it out. It's literally just a short hop, skip, and a jump. Okay. Soul Nebula is another stellar nursery, but it's got a very different look. It's gorgeous. Let's do an identification here. There it is. Yep. The Soul Nebula is big. And we'll bring this up into the view. I can get rid of this. Well, actually, I'm going to do this and set the target name. Okay, and there's the cluster in the middle of the Soul Nebula. Lady Astrid's asking a question. It is, why do Earth orbiting satellites such as Starlink not show up on feeds from Terra based elsewhere? Oh, they certainly do. We just got lucky tonight. We haven't seen any. But that is because we're looking at high inclination objects. If we're looking at the equator, all right, or mid-range or above and below the equator, we would see tons of satellites in our images. So we just got lucky tonight because we're looking at very high northern latitude objects. But normally we would see them, Lady Astrid. Hey, look who's here, Ronald. Ronald's one of our famous supporters. He's world famous. Oh, you're welcome, Lady Astrid. Okay, well, I think we're in a good place now. And we'll make this a 25-second shot because we don't need to go any longer than that with this, because this telescope will show all the detail in this nebula. Okay, let's go to our live stack. There's the Gamma Cass Nebula with Navi, Gamma Cassiopeia there. That is up on the server already if you want to go check it out by going to skytourlive.org and scrolling down and checking it out. If you go to skytourlive.org, you can make a donation if you want to help us out. We would really benefit from it. Let's pull out here. Okay, there is the Sol Nebula right here. Let's go back here. Let's color correct it. And let's also do this. Boom. Look at that. We have lots of nebulous detail here. I'm going to take our dark level, move it up the slope to just shy of the peak. Look at that. Okay, now remember what I told you about young hot clusters? Here's a young hot cluster. Look at this opening here. This is a cavity that this young hot cluster has blown open in the middle of space here. And its radiation is pumping out and pushing out it's pushing out the material in there. The dark dust is more dense, less hard, less easy to push. The hydrogen gas, as you can see, very, very light, lightest stuff in the universe actually, and it goes all the way out to the fringes for the most part. So the cluster is lighting that stuff up and causing it to glow. Remember, we're seeing the universe in 3 dimensions, so we could be seeing it kind of from one side, and this may be totally symmetrical to this if you look at it, but from our point of view it may look off, like this is to the side. In fact, it may be right in the dead center for all we know. Very cool. Yeah, it's gorgeous. Oh yeah, I just can't get over the color rendering. The color rendering is so much better. If we were shooting this in black and white, this is how it would look. See, that's without color. And if we do 3/4 color, it'd be kind of like this. Wouldn't be that bad. But if we do it at 100%, then we get the richness that the universe has to offer. Really pretty. Now if we overprocess, we can see what's hiding back there. Oh, a lot of stuff hiding back there. A lot of dark nebula, a lot of dark lanes. Those will all be visible. And we can't get away from satellites. You asked about satellites. Well, there's one right there. Yep. This is a high inclination satellite, probably a spy satellite. So it's going over the pole, and we're seeing it just by chance. Here is a dark region in our overprocessed version of this right now. Right there. That could be a gravitationally collapsing area. And there could be stars forming in there, possibly planets. Let's bring this down a little bit. Make it a little more. I still have this on high, so that's what I'm doing that on purpose. But you can see this one very, very dark area here. That's a very dense area. So the temperature in there is going to still be very cold. Okay. If you guys are having a good time, make sure you hit the thumbs up, okay? Give us a like. Like I said, no one's doing this out there like we are, We stream multiple objects at once. I know that other people are streaming and doing astronomy too, but no one is actually streaming the universe like this and teaching you about what you're looking at in the sky like this, taking you through the formation of the universe every night. Ronald asks, am I going to Bill's? Bill's my producer for KGRA, and he's out in New York State, and yes, I'll be going there Saturday. I'm going to be visiting on Saturday. Yeah, so this is also called the baby nebula, and you can see the head of the baby here and the mouth and what looks like a hand. I think it looks like the Star Child from 2001: A Space Odyssey. LCX-19 from Snowflake, Arizona. I've been in Snowflake. I've been in Heber. How's it going? It's kind of chilly in Snowflake right now, actually. One of my nonprofit people is up there right now. See, yeah, Lady Astrid, it does look like the Star Child. It does. And it's really pretty. Yeah, it's cloudy right now up there, yeah. I think the temperatures are in the 30s, and it's kind of nasty there right now. But then again, you're at like 7,500 feet, right? In Snowflake? Maybe higher? Maybe you're over 8, actually, in Pine Top. I go to Pine Top a lot. I'm actually in Connecticut, but I actually went out there to see if maybe a telescope in the Pine Top region would be nice, but I opted to not do that because you're 5,600 feet there. Okay, I opted not to do it because, as it turns out, the skies are not clear for enough days of the year there to merit putting a telescope in. Hey, there's Daryl. How you doing, Daryl? Daryl must have got his Thanksgiving stuff done. All right. Okay. Well, there we go. And so let me annotate this and get the annotation saved. Here we go. All right, so that is our last object tonight, guys. I hope you have a great Thanksgiving. I am going to head to bed now so I can get up really early. I don't want to, but I got to. I can stay up all night and do this. I have, actually. And really messed with my schedule. But sometimes it's beautiful. you know. And when it's that beautiful, sometimes you just got to do it. So, hello, Hunter. My son just got back from work. He works at Channel 3, the largest TV station in the state of Connecticut. And he's usually all over the state on a nightly basis. Let's see. ERT radio is Ronald. He says, my postal lady made an apple pie for me. It will take me a week to eat it. Very good. All right. Well, that's fantastic. I hope you guys have a good evening, a good day tomorrow. And with the new moon coming, we're definitely going to stream again soon. And we'll pick up a batch of new objects, visit some old ones to do updates like the supernova in the galaxy. And I just hope you guys have a good time tomorrow. So I will see you all later. And, you know, if you go outside, look up and say, it's a big time machine, right? As Greg O'Brien was talking about earlier, he was absolutely on the money. It's a big time machine. When you look up there, you see it as it was. You never see it as it is. Isn't that incredible? All right, guys. Lights out, and I will talk to you the next time. Good night, everybody.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views.